In section 10.3, we're going to look at what are called hyperbolas. Notice they're a special curve and they're shaped like arches. Again, we're going to have a lot of similarities between a hyperbola and a ellipse. They look very similar. The idea is instead of pointing inward on itself like an ellipse, we're going to point outward is the difference with a hyperbola. We've got several important features, the first one of which is the vertex. The vertex is, notice, along our axis of symmetry. Remember what an axis of symmetry means back from when we talked about parabolas, is it's a axis where if you cut your graph along that line, you'll get the same picture. In this case, on this first example, above and below. It acts as a line of symmetry. And notice we have something new called a directrix. We will talk about that in a little bit. Notice they're dotted lines. They look similar to an asymptote. And we'll talk about eccentricity again. It'll be a little bit different than what we did in the ellipse back in section 10.2, but it'll be a similar idea. Notice that the hyperbola, though, is an open curve, meaning it doesn't have any ends and it keeps on going forever. On all the ends, you keep on seeing that it's heading towards infinity in either direction. It's an open curve. So how do we come up with the shape of a hyperbola using an equation? So again, there's going to be something called the standard form of a hyperbola. It will actually look very similar. The equation will look very similar to what you have in an ellipse. Notice if you go down, you'll see an x squared and a y squared. You still have an a squared and a b squared, and you still have that equals 1. The huge difference between an ellipse and a hyperbola is that instead of a plus in the middle, it is now a minus. That is the only way to know the difference between a hyperbola and an ellipse. Now, because of the minus sign, it does matter which comes first and which comes second. For this first set of examples, we're looking at, notice our hyperbola on this first set of examples points out to the right and points out to the left. With our foci, notice we still have foci, or two focuses, go out along the x-axis. They're going left and right. And the reason being is because x is going to be our major axis, which is why the x is coming first in your equation. So whichever one comes first before the minus sign is your major axis. It's not necessarily which one's bigger or which one's smaller like it was with the ellipse. But just like the ellipse, the center is found the same way. It's whatever was with your x and your y, but you take the opposite sign just like you did with the ellipse. Because our x came first, that's why our vertices are left and right of the center. Again, it's not going to be called a radius, but we'll treat it like that. The radius for the x's will go left that amount and right that amount from the center. Those will create your vertices that start off your hyperbola here. Your foci are again on your major axis just like before. And they're found the same way by adding and subtracting the c. Notice they actually push you out further than the graph, and they'll still be inside the graph just like before. However, notice your formula to find c is actually different. Last time with ellipses, you have a squared minus b squared. Notice with hyperbolas, you actually have a squared plus b squared. Which is funny because the hyperbolas actually have a minus sign in it. So with ellipses, you have a plus between the x squared and y squared in standard form, but you have a minus in the c squared formula. Whereas with hyperbolas, you have a minus in the standard form equation, but in the c squared equation, you have a plus. So you get actually more of the Pythagorean theorem. A squared plus b squared equals c squared. Notice there are asymptotes involved in these graphs. Notice there's two of them. Notice they go through the same point in the center. The difference is the slope. They have the same slope, but one's got a positive slope and one's got a negative. Notice also that they do go through the center. So you have the H and the K here. Notice with the H here, it's actually going to be reversed just like it is in the formula. So you'll have whatever sign matches up with the formula over here. But the K is also, because it's on the outside, is actually going to be the opposite of what was in the formula. And then notice this B over A here, because it's going to be out in front of your X, this B over A is just going to be your part of your slope. That's why you have a positive and a negative on it, because there's actually two asymptotes, the one with the positive slope and the one with the negative slope. What we can actually do is create more of a box if we want to actually draw the asymptotes. It'll make it a little bit easier. And to create that box, what we'll do is we'll go up by B, down by B, left by A, right by A. So we'll go left by A, right by A, create the box and the asymptotes, and then we'll go up by B and down by B. Again, we always think of A as the radius of, in this case, whatever's coming first, and B will be the radius for your Y's, which is what's coming second. So, but this is